Review the examples that you just tried on your own. So you had examined each of these examples and looked for which kinds of improprieties each contains. So I'm just going to go ahead and quickly go through the answers so that you can check your responses. So the first type of impropriety is an infinite interval of integration, and all of the ones I'm circling here, there were 5 integrals here that, as you can see, have either an infinity as the upper limit of integration or a negative infinity as the lower limit of integration. And notice this one here has, in fact, both limits are infinite. The other type of impropriety that we discussed was when an integrand is unbounded over the interval of over which you're taking the integral. And this happens, as in the case here, where you have some sort of a vertical asymptote. You can see, as in this case, when the function is shooting off towards infinity, there's not a well-defined area here under the curve. So there were actually 3 different of these integrals that displayed those kinds of improprieties. That's basically the entire bottom row here of examples. And you can see that in each of these, the denominator of the integrand is 0 at x equals 0. And so there is, in fact, in these cases, there's a vertical asymptote at 0, and hence those are classified as improper. Another case where you might have these asymptotes, consider examples like natural logarithm, tangent, etc. All right. So we're going to be moving on now. So once you can recognize an improper integral, either graphically or formulaically, the next question is, how do we actually get the area under the curve, have a well-defined notion of area under the curve in that situation? And that's what this next section is about. And so what I want to do is focus on the example, as an example, the integral from 1 to infinity of the function 1 over x squared dx. Notice that this has only an infinite interval, so it does not have a vertical asymptote over the range that we're trying to integrate. So we're really going to work with that first kind of integral here, and then we'll expand into the second type of integral, improper integral. For this example, I want to start by thinking graphically, and to do that, I'd like to actually incorporate some Desmos here. I know that we had started our semester off with Maple, and I just feel that moving to an online distance learning situation, Desmos will actually be easier for demonstrations, and I think easier for you to access at home. However, I would still be very happy to help any of you that have Maple to work through any of the examples that we have using that program. Okay, so I'm going to go ahead and just open this file here, and in case you haven't seen Desmos, here's kind of an on-the-fly introduction. So this is sort of a Desmos graph setup, and so on the left-hand side, we have all of the commands that we're entering, and on the right-hand side, the graph kind of updates automatically, so it's really nice that way. And you can add little boxes here, which you can type different commands in. This first one here, I'll just quickly go through. The first one is just a text box, so it's where you can type your comments. The second one here is defining a function f of x. When you start typing, you kind of start typing in calculator notation, and Desmos kind of interprets it for you, and you can fix it. So we can practice doing several of those at a later time. I just want to kind of show you what's here so that you can practice updating for this example. In box number 4 down here, I've put in the integral of f of t dt, and now because f was defined up here in box 2, Desmos is going to be interpreting this expression using that f that I've defined. So it's really thinking about 1 over t squared here. And then I've put in variables for the limits of integration, and those are defined. So a is defined down here in box 5 as 1, b is defined as 4 in box 1, and then this last box down here, number 8, is just the code for shading in the purple area of the definite integral. So the first definite integral that we're evaluating is from 1 to 4. You can see here that that's the shaded purple region under the curve in the graph. And the other thing that you can see here in box 4 is you actually see what that integral evaluates to. So in fact, it's 0.75. Something fun here is that Desmos does these sliders really easily, so I can actually just grab this slider, and you can see as you drag it that the purple area is increasing in the graph as b, the value that the upper limit of integration, is changing. And also up here, notice in box 4, the value of that definite integral is getting updated real time. So you can see that as you move b, okay, if it starts at 4 here and you start moving it up, you can see that the area is increasing, which is what you would expect because the graph all lies above the x-axis. So as you make your interval bigger and bigger, that number should also get bigger and bigger. And you notice here that b equals 8 gives us an integral of 0.875. So I'm going to go ahead and just record those couple values here in our, let's see if I can switch applications. There we go. I'm going to go ahead and record those values. So we know that the integral, so we want to know something about the integral from 1 to infinity. So let's consider the integral from 1 to 4. So this is equal to 0.75 we saw from Desmos. And we ran the integral from 1 to 8. Whoops. 1 to 8. And that was 0.875. And so we can see that these numbers are increasing. The question is, as we bring those numbers, make them larger and larger and larger, are they approaching some area that we could say is the area from 1 to infinity? So go ahead, go back to Desmos, and maybe pause the video right here. Go back to Desmos, put in some really large values of b, and make a conjecture. So in particular, if you do go to Desmos here, you can just click on b, and you can add some zeros if you like, and hit enter, and then Desmos will give you the new integral for the value of b that you've input. We'll also shade, although in this case the graph, we don't see enough of it to get all of it in here. And so the shading goes from 1 to 80 here, and the total amount is 0.9875. Okay, and so what we might conjecture then is that that these quantities, as we increase the right endpoint of our interval, these quantities are getting closer and closer to the number 1. And so that's our conjecture that we will need to make rigorous and check. Okay, so how are we going to check it? Let's consider the let's frame this question in terms of limits. So let's consider the integral. So let's fix sum b greater than 1. So, and then we'll look at the integral from 1 to b of 1 over x squared dx. Okay, and let's go ahead and evaluate this. So this is the same as rewrite the integrand as x to the minus 2. And that's easy to work with using just the power rule for integrals. So we'll go ahead and do that. We add 1 to the power, so we end up with x to the minus 1, and we divide by minus 1. And then this is what we are going to evaluate from x equals 1 to b. So plugging in here, we have negative 1 over b plus 1. Or in other words, 1 minus 1 over b. So then, if we consider, whoops, so consider the limit as b goes to infinity of the integral from 1 to b of f of x dx. This is just going to be the limit as b goes to infinity of 1 minus 1 over b. And that's, of course, just 1 because 1 over b goes to 0. By the way, notice, this is something I should have pointed out a second ago, notice that we can kind of use this calculation we did to find the integral from 1 to b. We can actually see that, in fact, that checks out here, because if we're considering our upper limit of 4, right, 1 minus 1/4 would be 3/4, and that's exactly what we have here as the result from Desmos. So it's nice to kind of make those checks every now and then. Okay, so we now have this limit, and so when this limit exists, this is how we will define the improper integral. We'll define it to be this limit. Okay, so I'm going to go ahead and switch colors here. So this is equal to the integral from 1 to infinity of f of x dx. Okay, so what I'd like for you to do now is go through a similar procedure here and work through the similar functions in activity 6.5.2, and then there's some kind of bringing it together questions. So you'll be working with the function integrand 1 over x and also 1 over x to the 3/2. Okay, we'll go ahead and resume the next video discussing those problems.